Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the early decades of the 20th century, the science of geology rested upon a foundation of fixism. The continents and oceans were largely perceived as permanent, immutable features of the Earth's surface. Their positions established since the planet's primordial cooling, explanations for geological phenomena adhered to this static worldview, with vertical movements like uplift and subsidence accounting for mountains and basins. The bewildering coincidences of geology and life across vast oceanic expanses were explained away with elaborate, ad hoc hypotheses of sunken continents and transoceanic land bridges, conceptual crutches for a paradigm straining under the weight of accumulating evidence. Into this intellectual landscape stepped Alfred Lothar Wegener, a German meteorologist and polar explorer whose 1920 publication, The Origin of Continents and Oceans, presented a theory of breathtaking scope and revolutionary implication. Wegener proposed a world of motion, a grand horizontal displacement of the continents over geological time. His work was a masterpiece of interdisciplinary synthesis, a unified explanation for a suite of disconnected puzzles that had long troubled the world's naturalists. Wegener's case began with the most intuitive piece of evidence, the geomorphological congruence of coastlines. While others before him had commented on the casual, jigsaw-like fit of South America and Africa, Wegener elevated this observation into a scientific argument. He moved beyond the fluctuating shorelines, focusing instead on the true edge of the continental blocks, the submerged continental shelf, specifically using the 200-meter isobath. When these more stable boundaries were compared, the fit became astonishingly precise. The prominent eastward bulge of Brazil nestled perfectly into the Gulf of Guinea, and the smaller re-entrants and promontories along the opposing coastlines found their counterparts with uncanny accuracy. This was a geometric argument, suggesting the continents were once a single, contiguous landmass that had been fractured and pulled apart. For Wegener, this was the initial, arresting clue that the Earth's surface possessed a history of profound lateral movement. Building upon this geographic fit, Wegener marshalled powerful geological evidence. If the continents were once joined, their geological structures should show continuity across the modern oceans. He found precisely this. The ancient rock formations and mountain ranges of opposing continents appeared to be fragments of once unified geological provinces. A compelling example was the Cape Fold Belt in South Africa, a formation of distinctive character and age, which aligned perfectly with the Sierra de la Ventana range in Argentina, when the Atlantic was conceptually closed. An even more dramatic correspondence existed in the Northern Hemisphere. The Appalachian Mountains of eastern North America, with their specific geological history and structural trends, pointed directly toward the Caledonian ranges of Ireland, Britain, and Scandinavia. These mountain systems shared a common age and tectonic origin, forming a single, immense orogenic belt before the Atlantic Ocean opened through its center. Wegener argued that these were geological scars, evidence of ancient continental collisions, now separated by thousands of kilometers of ocean. The fossil record provided what was perhaps the most compelling line of reasoning, as it involved the very distribution of life itself. The fixist model required organisms to have crossed immense oceanic barriers, an impossibility for many species. Wegener highlighted several key fossil distributions that defied such an explanation. He pointed to the remains of Mesosaurus, a small, freshwater reptile from the Permian period. Fossils of this creature are found exclusively in sedimentary strata of Brazil and South Africa, and nowhere else in the world. The notion that this small coastal or riverine animal swam the breadth of the Atlantic Ocean was biologically untenable. Similarly, the distribution of the seed fern Glossopteris presented an insurmountable problem for the static Earth model. This distinctive plant is found in Permian rocks across India, Australia, South America, Africa, and even Antarctica. Its seeds were heavy and unlikely to be dispersed by wind or water across such vast modern distances. The only parsimonious explanation was that these landmasses were once united in a single supercontinent, allowing species like Mesosaurus and Glossopteris to spread across a continuous territory. Finally, Wegener assembled a powerful case from paleoclimatology, using ancient climate evidence to deduce the past positions of the continents. He identified deep paradoxes in the geological record. Late Paleozoic glacial deposits, including characteristic scratched bedrock and compacted tillites, were found in modern tropical and subtropical regions like India, the Congo Basin, and southern Brazil. Under the fixist model, this implied a global ice age so severe that glaciers reached the equator, a scenario contradicted by evidence of concurrent tropical conditions elsewhere. Wegener offered a more elegant solution. If these continents were clustered together over the South Pole, they would naturally experience glaciation. Conversely, he pointed to the existence of extensive coal deposits formed from lush tropical swamp vegetation in high-latitude locations like Svalbard and Antarctica. These regions today are frozen wastelands. The geological history, however, spoke of a past spent in warmer, equatorial climes. Wegener's theory of continental displacement provided a singular, coherent mechanism to resolve these climatic enigmas. The intellectual groundwork for a southern supercontinent had been laid by the Austrian geologist Eduard Suess, who named it Gondwanland based on paleontological links. Suess, however, envisioned parts of this landmass foundering and sinking beneath the waves. Wegener's contribution was the radical concept of displacement, of continental drift, a dynamic process of horizontal cleavage and movement. It was this vision of a mobile Earth, built upon a consilience of evidence from geography, geology, biology, and climatology, that marked the true genesis of a scientific revolution. While the assembled evidence presented a compelling case for a mobile past, the theory's acceptance hinged entirely on a plausible physical engine for such planetary rearrangement. Alfred Wegener, in The Origin of Continents and Oceans, ventured to provide one. He proposed two primary geophysical forces to propel the continents. The first, which he termed pole-flat or pole-freeing force, arose from the planet's rotation and equatorial bulge, supposedly impelling the lighter granitic continents toward the equator. A second, a westward precession, was attributed to the gravitational tidal drag of the Sun and Moon acting upon the viscous terrestrial crust. He envisioned the continents, vast rafts of sile, ploughing through the denser, more fluid basaltic ocean floor, the seamer. In this mechanical explanation, however, lay the theory's fatal vulnerability. The undoing of this proposal came from the unforgiving realm of geophysics. The eminent British physicist Sir Harold Jeffreys performed a rigorous quantitative analysis of Wegener's proposed mechanics. His calculations, presented with devastating clarity, demonstrated that the pole-fleeing force and tidal drag were deficient by many orders of magnitude. The forces were millions of times too feeble to overcome the immense frictional resistance of the oceanic crust, which geophysicists understood to possess the strength of a rigid solid. To move the continental blocks through this material, Jeffreys famously concluded, would require forces powerful enough to hold the Earth's rotation entirely within a year. The proposed engine was physically impossible, a conclusion that armed a generation of geological authorities with the ammunition to dismiss the entire hypothesis. The opposition, especially among American geologists like Bailey Willis of Stanford University, became particularly trenchant, casting continental drift as a geopoetic fantasy unmoored from the hard rock realities of structural geology. Decades passed with Wegener's ideas relegated to the fringes of respectable science. The first glimmers of vindication emerged from a wholly new quarter during the 1950s. Studies in the field of paleomagnetism, spearheaded by physicists like Stanley Keith Runcorn and Patrick Blackett in Britain, yielded astonishing data. By measuring the remnant magnetism locked into iron-bearing minerals as they cooled and solidified, these scientists could determine the latitude at which the rocks had formed. These fossil compasses revealed that continents had experienced profound rotation and latitudinal shifts relative to the Earth's magnetic poles. The rocks of Europe, for instance, contained a consistent record of a northward journey spanning hundreds of millions of years. This provided the first independent, quantitative confirmation that Wegener's core claim of immense continental displacement was fundamentally correct. The continents had indeed wandered. The missing mechanism, the engine Jeffreys had rightly demanded, arrived with the systematic exploration of the ocean depths. Post-war bathymetric mapping, a direct beneficiary of Cold War naval technology, unveiled the planet-girdling system of mid-ocean ridges. Building upon this new topography in the early 1960s, Harry Hess and Robert Dietz independently formulated the elegant concept of seafloor spreading. They proposed that new oceanic crust was continuously generated at these volcanic ridges, pushing the older crust and the continents embedded within it away on either side like colossal conveyor belts. The continents were passive passengers on a dynamic seafloor, a far more plausible scenario than Wegener's vision of them ploughing through a static crevice. The definitive evidence for this conveyor belt arrived in 1963. Frederick Vine and Drummond Matthews, along with Lawrence Moy working separately, synthesized seafloor spreading with another recent discovery: perplexing magnetic stripes of alternating polarity arranged symmetrically on both sides of the mid-ocean ridges. They hypothesized that as new basaltic magma welled up and cooled at the ridge, it recorded the orientation of the Earth's magnetic field at that moment in geological time. Since the planet's magnetic field periodically reverses, the ocean floor became a vast magnetic tape recorder, preserving a perfect, unmistakable chronicle of its own creation and expansion. The Vine-Matthews-Morley hypothesis provided the incontrovertible proof the continents were moving because the very ground beneath them was in constant motion. This extraordinary cascade of evidence culminated in the work of Canadian geophysicist John Tuso Wilson. He brilliantly synthesized continental drift, seafloor spreading, and an understanding of transform faults into the comprehensive and unifying theory of plate tectonics. Wegener's original concept of displacement was now a core component of a robust, mechanically sound global system that explained earthquakes, volcanism, and mountain building with breathtaking coherence. Alfred Wegener's singular vision, born from a heroic synthesis of disparate clues, stands as a testament to the power of consilience in science. He provided a revolutionary what long before technology could reveal the how. His intellectual odyssey illustrates a profound truth about scientific progress. A correct, elegantly simple idea, though initially assailed for lacking a mechanism, can persist through decades of skepticism, waiting the crucial data that ultimately transforms it from heresy into the foundational paradigm of an entire field.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.